Hello everyone, welcome to the talk Unearthing the Impact of Sanitize on Performance and Latency in Embedded Storage. My name is Sumit Paul. I work as a senior manager in Samsung Semiconductor. Along with me, co-presenter Shankar Sneaker work as a senior staff engineer in Samsung Semiconductor India R&D. We both work in a team which deals with the product qualification and customer service. In our day-to-day life, we get a lot of queries, observation on performance and latency in embedded storage, and in this presentation, we'll be covering few such issues and with the resolution provided for such issues. Let's go to the outline and see what is the agenda today. In the agenda, we'll be talking about evolution of embedded storage. We'll be talking about garbage collection and its influence on performance. Then we'll be covering sanitize. Then we'll be moving to use of discard as a mount option, and then we'll conclude the talk. The evolution of the embedded storage. These slides talk about the evolution of embedded storage over the years. Here we have not added the very old generation of multimedia devices. eMMC 5.1 is very commonly and most used embedded storage. Applications like mobile, set-top boxes, automotives, and many more still using these embedded devices because of its low power, moderate speed, and many security features, and of course the low cost. Now, numerous devices are generating big data. There is a seamless evolution on the network side with 5G getting adapted very fast. New UX, AI, triple cameras, Ultra HD 8K displays, autonomous car need to process a lot of data, which raise the need for high bandwidth storage with high reliability and with low power consumption. And that's how the UFS got adapted very fast in this high-end segment. UFS keep evolving, and currently we are using third generation of UFS, and next one is already under development. If we look at the speed of these devices, eMMC provides a max of 400 megabyte per second with half duplex parallel interface, whereas UFS already providing a 3 times faster performance, that is 1200 megabyte per second with full duplex serial interface with two-lane setup. And the current generation which we are working on, that is UFS 3.1, provides a 2.4 gigabytes per second, and coming generation, that's UFS 4.0, which is still under development, which certainly will be providing much higher bandwidth. And these UFS devices will be used in various market segments. Let's go to next slide. So in this slide, UFS actually on the side is being called as SSD for multiple segment due to its comparable speed with old generation SSDs. UFS has many notable advantages as shown here. To start with, its high performance, low power, asynchronous protocol, and many eMMC features specially curated for embedded market are taken as in UFS. UFS devices have a low EMI due to its differential signal. It has a well-known SCSI command set, ultra-fast booting capabilities, and automotive grade reliability, which makes UFS device to work and very extended temperature range. This all feature makes UFS as one of the best candidate for many segments of market, ranging from mobile, computing, automotive, gaming, Chromebooks, set-top boxes, surveillance, and many more such devices. Let's move to the next slide where we'll be talking about the garbage collection. Before going to sanitize, let's understand what can impact performance, latency, and one of the major reasons that is garbage collection. Let's quickly understand what garbage collection is. Garbage is written data on the flash which is no longer needed by a host, or we can say that it's a invalid data. What makes a garbage? Two major things. One of them is overwrites, other thing is discard. In flash, as we know, overwrites generally mean picking up a new location to write data and invalidating the old data, which means the data remains in the flash until there is a need to remove it or host specifically want to remove physically. Now let's understand what is garbage collection. Garbage collection is a very important feature to maintain device longevity and functionality. Garbage collection is needed to obtain free blocks to accommodate new writes. How garbage collection happen? This process involves movements of valid pages from source block to the destination block, and source block is picked based on the number of valid pages in the block, which means The minimum number of valid pages in the block mean the minimum GC cost. That's mean the time taken by the garbage collection will be minimum since the number of pages which has to move from one block to another blocks are very less. If we take example in this picture, block 0 and block 1 has few invalid pages and few valid pages. Now host has to write new data and there is a need for some free blocks. Now what will firmware do? It will trigger a garbage collection, and as part of garbage collection, we'll be taking some time slice from the IO operation and we'll be moving the valid pages data from block 0 and block 1 to the new block, that is GC destination block, and this way we'll be freeing up two new blocks called block 0 and block 1, and we'll be occupying one new block. So this process is called garbage collection. Let's move to next slide. In this slide, we'll be discussing major elements which cause garbage collection and which eventually impact the performance. Three major elements which actually decide the intensity of garbage collection is free bit count, valid page ratio, and over-provisioning. If in a device, OP blocks are more, which means there is enough margin to accommodate invalid pages in the device, and that result in lower write amplification factor and a higher performance. On the other hand, in embedded devices, OP ratio is not very high. That means if free block count in device is reaching the threshold very often, then device has to go for garbage collection, and degree of that garbage collection is decided by the host pattern, valid page ratio, and the free block count. This garbage collection actually impacting the user experience in multiple ways, as sometimes app not responding, app launch time is increased, and many times lag in operation or slow copy of file have observed. Here example, wherein a device which was executing with random host pattern, and after certain loop of execution, device went to garbage collection and performance drop is observed, and this caused a very high latency. So we'll be further slides we'll be talking about how to avoid these kinds of issue. Let's move to the next slide. So here is the comes the main part of the talk. It's called sanitize. In the next slide, we'll be talking about the myth about the sanitize. Use of sanitize or purge only as a security feature. In embedded storage, MMC and UFS, commonly known purpose of sanitize or purge is to rendering the data on the media invisible to recover for a given level of effort. The use of sanitize operation requires the device to physically remove the data from unmapped address space that is based on the secure removal type. In current EMC or UFS spec, the secure removal type is one of the deciding factor which tells the intensity of sanitize. If this factor is chosen correctly, it will be physically removing the data or it will be physically removing only the metadata. As part of sanitize, FTL performs scan of each block and move valid pages to another free block. Operation repeated until there is no invalid pages in the user block and erase all the unmet blocks in the end, which creates a very high secure feature of sanitize. That means data cannot be recovered at any point of time. And in the last, sanitize and purge are host-driven method to sanitize the device as per the privacy requirement developed to meet standard guidelines by some governing bodies. There is many governing bodies which want these features to be part of all the storage devices where this data is need to be very securely erased so it cannot be recovered for any unwanted use cases. Let's move to the next slide. In this slide, we'll be talking about sanitize and its concealed feature. Seasonable use of sanitize help in reducing the latency, enhancing user experience with the application and improving the performance. Sanitize utilized in accordance with the storage developed device policy, which significantly improved the QoS, that is better consistency and predictability of latency and performance while serving read-write commands. So below are the major feature or major things we need to understand before using a sanitize. Sanitize will improve the performance latency, which we'll be seeing in the further slide. Security, which is the main important feature of sanitize, is already discussed in the previous slide. And third important part of this is lifetime. Since the region being operated on is not accessible by the host, application requiring this feature must work with the individual device manufacturer to ensure this operation is performing properly. Since this feature impacts the device reliability, when we do a sanitize operation actually take a blocks which are invalid, which having a invalid data, move that invalid data to the new blocks, and this free blocks will be erased and put in the free block list. While erasing these free blocks again and again will impact the device lifetime. So using the sanitize in according to the device policy is very important. So in further slide, we'll be seeing that real world experiments and few of these results which will help in improve the performance and latency. And now I'll call upon Shankar Knikar who will be taking the further slides and discussing the real workload and another few features. Over to you, Shankar.
Thanks, Sumit, for the wonderful introduction and outline. Let's take a look at the real-world examples. It is broadly known that in an operating system, if any file is deleted, discard will be issued to the underlying storage device. When user deletes the file through the operating system, it is not physically deleted from the storage medium. In fact, this file data is marked as invalid but remains in the unmapped address space. In another instance, when host performs overwrite on the previously written logical space, and then this previously written memory space can be invalidated by discard operation. These all cases may create a lot of fragmentation in the device and eventually make the system slower. That is, user will start seeing lag in the application, performance drop, high latencies, etc. In order to handle this unmapped address space effectively, from the customer issues familiarity, we conducted a study how effective use of sanitize and discard helps in achieving better QoS. For this study, we have taken two different system workloads, one from the automotive system running on Linux and another one from mobile system running with Android operating system. These workloads are captured during instances where customer experienced high latencies and high ANR respectively. Let's move to the next slide. In this slide, we are going to discuss on the automotive pattern. Experiments were performed on the state-of-the-art automotive chipsets from the tier 1 customers where pattern was host has written OS image, mostly Linux in this case, to the device as a pre-written data, which is a kind of read-only. And in the remaining area, host keeps on updating the same address range and performs a reboot after n number of cycles. First image shows the return pattern of the host where after 50 cycles of the boot, there is a discard performed on the full user area. From the plot, it's indicative that there are a lot of overrides and these overrides creates a lot of invalid space in the underlying storage. We have plotted the discard address range against the write address range and it is evident that discard was not covering much of the return address range. It was kind of a blind discard. Second image shows how continuous overrides on the same address range creates fragments inside the device. For this, we have captured firmware internal metadata from the device and plotted valid pages from the firmware internal context. It is observed that after approximately 1800 cycles, valid pages scattered across the physical blocks. Due to the above condition, free block count in the device reached the below threshold, triggering urgent garbage collection condition. In order to cater the incoming write operations effectively, device needs to perform urgent GC operation as GC will be performed in the slice of IO operation causing high latencies. Let's move to the next slide where we can take a look at the mobile pattern. In this instance, host system has observed high ANR. ANR refers to the application not responding. For this analysis, we have captured the IO traffic with the help of protocol analyzer and the internal metadata of the firmware using proprietary tools. According to the analysis, host has pre-written OS data, mostly Android in this case, and in the remaining free area, user-based IOs are commencing. From the figure 1, host is using variety of chunk sizes for its IO operation ranging from 4 KB to 1024 KB. With the help of internal metadata, we plotted valid page distribution and it is observed that valid pages are distributed across the device. As host is using different chunk sizes and mix of sequential and random address ranges cause the scattering of the valid pages in the storage system. Due to this scatter of valid pages, underlying storage has reached free block count less than the threshold, which forced the firmware to enter into a garbage collection condition. Underlying storage system in this case was eMMC working in the command queue mode from the PA log or the protocol analyzer log. we observed that tasks were delayed in getting ready as Perform was performing urgent GC condition to serve the incoming IOs effectively. Due to the ongoing GC inside the storage device has caused the high ANR. Next, move to the slide where we are going to talk about how Sanitize can be effective in mitigate the high latency condition. For this, we have detailedly analyzed automotive pattern. Here, we are going to discuss on how seasonable use of Sanitize based on the host pattern and the fill ratio. Fill ratio is nothing but the VPC distribution helps in reducing the higher latencies by freeing up of the blocks. On the left image, it is evident that FP count is dropping as host is performing continuous write operation. Mainly in this case, it was overwrite operations. So FB count has reached from the significant high count to reaching a threshold where firmware has to perform GC to free up the blocks. From the graph, it is evident that fill ratio is 50%, means approximately all the blocks have valid pages for half of the blocks and remaining pages are having invalid data. This condition is reached because of lot of overrides. As device is in the urgent GC condition, max latencies are observed as pointed in the right top corner of the graph. Now, we requested host to perform sanitize seasonably and we captured the metadata from the device in the regular intervals to analyze the storage behavior. When storage receives sanitize command from the host, FTL performs scan of each block and moves valid pages to another free block. And this operation is repeated until there is no invalid pages in the user block and erase all the unmapped blocks. During scanning of the blocks, storage device will assert a busy and it's recommended not to interrupt the ongoing sanitize operation by issuing any high priority interrupts. Coming to metadump analysis, which summarized on the right side, we have observed that FP count was increased significantly after the seasonable usage of sanitize operation, with fill ratio as of the original condition. After the use of Sanitize, host did not see any latency instances as enough free blocks are released to the pool. This has helped to restore the performance and QoS of the storage system. Next, move to the next slide, where we are going to discuss on the one of the triggering condition or one of the condition where host has to issue the Sanitize operation, that is BKOPS flag. From the JEDEC specification, BKOPS is one of the features storage system has to support where device will indicate its need of performing backups to the host in the response packet. Once the backups is raised by the device, we request host to perform sanitize in the idle time. As discussed in the previous slide, once device performs sanitize based on the host request, there is substantial amount of free blocks are released to the blocks pool and there is significant improvement in the latencies. And the subsequent write operations did not see any high latencies. From the above studies, it is evident that enough free blocks are released to the pool, increasing the better QoS of the storage. Next, move to the next slide. In this slide, we are going to discuss on the benefits of discard operation with respect to the storage system. Here, as we know, if any file is deleted, discard will be issued to the underlying storage system. When user deletes file to the operating system, it is not physically deleted from the storage medium. As a matter of fact, this file data is marked as invalid and remains in the unmapped address space. Again, from one of the automotive customer host pattern, below analogy can be drawn. Image on the left. If you see the image on the left, there is no much of impact of the discard because the old data was already invalidated due to the overwrites as same as it's discarded. On the right side of the image, it's one of the ideal condition where the discard is very helpful. If you see this image, if the host writes new data to the shifted logical address, then old data is still remained in the valid data, even it is old content for the host system. In this condition, discard is very helpful to make up the free space. There are two approaches for sending the discard command to the mounted file system. The first method is fstream command. This is a host initiated method where discard is sent to the unused blocks on the mounted file system. This can be a batch block based discard method and it is offline way of performing discard operation. Second method is discard as one of the mount parameters. This can be done by adding discard option in the etc fs tag. This is more of file system controlled whether it has to issue discard to the underlying blocks when blocks are free. This is more of an online method and sending discard to the blocked device. Next comes to the advantage of sending discard. The main advantage of sending discard is reduced GC cost. If storage receives the discard command, the FTL marks pages which belong to discard command as invalid. Because pages marked as invalid are not copied to another place during garbage collection, as a result, the discard command significantly reduces the garbage collection cost. As GC cost is reduced, this will helpful in the improved performance of the device. Mainly, random write performance was increased significantly with the appropriate and seasonable use of discard. Next is the increased lifetime. Yes, GC cost reduced, which means fewer valid pages movement, which helps in the increased lifetime. Next, move to the conclusion of our study. Okay, let's conclude this session with key takeaways. Okay, how the close collaboration between host and storage device can improve the performance, latency, and lifetime of the embedded storage device is demonstrated. As a result, two main characteristics of the underlying storage device is exhibited. First, the usage of discard as mount option reduces the fragmentation significantly and eventually the backups time and occurrence of the garbage collection. Second, the seasonable use of Sanitize to improve the random write latency. As a result, we confirm that our methods improves the random write latency of the storage significantly. As it is already established and being used by many customers, and we are certain that the analysis and the proposed method can be used by any host developer to optimize the random write performance and latency and lifetime of the storage device. Thank you for your valuable time. In case of any queries, please reach out to me or Sumit.
Thank you.